Now, let us go to the other interaction, which is basically the weak interaction. We already listed the elementary particles known to us. Let us write down again that here elementary particles. We have electron. Let us explicitly write down the left-handed and right-handed ones, and we have nu El corresponding to an electron. We have left-handed muon, nu mu L corresponding neutrino, left-handed tau lepton and nu tau L, and we have right-handed electron. There is no right-handed neutrino corresponding to that. We have right-handed muon, we have right-handed tau particle, and we do not have any right-handed neutrinos. This is because they are not found. In experiments, we have not found right-handed neutrinos. We have only found left-handed neutrinos and right-handed antineutrinos in beta decays and other weak interactions. What about the quarks? We have UL, DL, Cl, the charm quark, strange quark, left-handed, top quark, left-handed, bottom quark, left-handed. We also have right-handed quarks, all of them, Cr, Sr, top and bottom, all of them are there. And again, what is observed is that only left-handed particles take part in weak interactions. This is an observation, experimental observation. Now, to conform to that, we consider the weak interaction and the gauge transformation corresponding to the gauge weak interaction. The gauge group is identified after some studies as SU2 gauge group. SU2, since only the left-handed particles transform under SU2 weak interactions, I consider we will write the gauge group as SU2L. L just denoting that to remind us that only left-handed particles take part in this. And we can club these particles together, okay, or psi corresponding to the left-handed neutrino, psi corresponding to the electron can be clubbed together and considered as a doublet under SU2L. Whereas, the right-handed field has no such partner and the wave function corresponding to that, or the field corresponding to that is a singlet under SU2L. When I say singlet, which means that it is invariant or do not take part in the interaction corresponding to SU2L, which is weak interaction. This is also similar to the isospin that we had discussed earlier. In the case of the flavor isospin, for example, we considered the proton and neutron as two different projections of the same object, which we could call as nucleon. We could consider something called isospin, and the isospin of nucleon is half, and plus half projection of that is proton, minus half projection of that is neutron. Now, in exactly the same way, we can consider here the SU2 L isospin or the weak isospin. This is completely different from the isospin that we had considered in the case of strong interactions, but let us call it isospin because that is basically a standard terminology now. So, under isospin we can categorize these fields, and we just now mentioned that the wave or the field corresponding to nu E L and E L transform as a doublet, which means isospin of this is equal to, let me denote this by I equal to 1 by 2, and isospin 3, the third component of nu E L is equal to plus half, and that of electron is minus half. Whereas, when we consider psi E R, we have a singlet, and the isospin of E R is equal to 0, and isospin third component is also equal to 0. That is why we call this singlet under SU2L. Similarly, other fields also can be clubbed. So, let us write that down. I will forget about the psi for the time being, because the notation is becoming too much more and more complicated or clumsy if I write all the labels. So, I will forget about psi here, write only the notation nu E L just to denote the corresponding fields. Similarly, we have nu mu L and nu tau L, the left handed ones, and all others E R, mu R and tau R are singlets. And in the case of quarks, we will club U L and D L, C L and S L, top left handed and bottom left handed. Right handed fields are all singlets, T R, let me start from the beginning, U R, D R, C R, S R, T R, B R. All these are singlets. Okay. So, this is how we club this, write this explicitly as the in terms of the multiplets under SU2L. That is one thing. Now, studies, a lot of investigation had gone into understanding the weak interactions using the gauge symmetry, similar to the quantum chromodynamics for strong interactions and quantum electrodynamics for the electromagnetic interactions. We will not go into the history or the details of all those studies, but discuss only the end product. And at the end we see that we have to consider the electromagnetic interaction and the weak interaction together. Let us call it electroweak interaction. Okay. Some kind of a unification between the electromagnetic and the weak interaction has to be considered for consistency, and the gauge group that we should consider is not just SU2, but a direct product of SU2 and U1. Let us call this interaction or the charge corresponding to that as hypercharge. SU2 is the same as isospin, weak isospin, whereas the weak itself is now to be considered as, to be understood as used under electroweak interactions. There is a mix up between SU2 isospin and hypercharge in both electromagnetic interaction as well as weak interaction. Such unification is not very unfamiliar to us. If you remember your school days, you will see that magnetism and electrostatics and electricity are taught as different topics, especially the magnetostatics and electrostatics. We have electric field giving rise to all electrostatics, the force and dynamics under that. Similarly, we have magnetic field B giving rise to magnetostatics. But at high energies or for moving charged particles, when the motion is or the velocity of the particle is large enough, so that we cannot neglect the effects due to this motion, then we cannot separate the electricity and magnetism from each other. We have to consider electromagnetic theory or electromagnetic interactions between charged particles, and Maxwell's equation follows. You see that changing electric field induces magnetic field, changing magnetic field induces electric field, etc. And then clubbing all these together, you realize that you have to discuss electromagnetic interactions rather than electric and magnetic interactions separately. Unification of weak and electromagnetic interactions is another step in this direction. So, we can think about weak and electromagnetic interaction as unified, considered to be a unified theory at sufficiently large energies, thinking in terms of moving charged particle has larger energy compared to charged particle at rest. So, we will not go into a further motivations in this direction, but tell that this is what we are going to consider. The symmetry group considered is SU2 cross U1, L to denote that only the left-handed particles are going to be affected by transformation under SU2, and Y to denote that the charge corresponding to U1 is what called hypercharge, denoted by Y. How do we assign this hypercharge? There is a consistent way of doing it. This is due to the fact that we need to get the electrodynamics from this thing. We will see that later, that we have to actually describe the photons from this one, right, because this includes electrodynamics. What are photons? As I said, photon now is a mixture of SU2L and U1Y gauge fields. It will be seen later clearly. But that tells us that the corresponding charges, quote unquote charges, are also related. This relation is given by the charge of electromagnetic interaction Q is equal to I3, the third projection of isospin, which is the charge corresponding to SU2 plus Y by 2, where Y is the hypercharge. Now, let us look at left-handed electron and neutrino doublet. Q of nu E L is equal to 0. We know that it is a neutral particle. I3 of this is plus half, and that is sufficient to fix y to be equal to minus 1. If I take y equal to minus 1, I have minus 1 by 2 in the second term of the relation above, and I3 is plus 1 by 2, total is 0. Similarly, for electron, Q is known to be equal to minus 1, I3 is equal to minus half, which again gives you y equal to minus 1. This indeed should be so. This is because all the multiplets, SU2 multiplet, will have the same hypercharge y. We will see how y is so when we write down the transformations. This is also the reason that we have written the neutral component as the first component, I3 equal to half, and the negatively charged E as the I3 equal to minus half. To start with, we would have wondered, if you were keenly observing it, why I wrote nu first and then EL second, and what would happen if the other way around, if it was the other way around. If it is the other way around, this relation would change, that is the only thing. But if we stick to this conventional relation, then basically we have this way of representing the doublet. There is no other way of representing the doublet here. You will also see that because I3 changes by 1 unit when you go from one component to another component, nu to E, in the same multiplet, the charge should also reduce or change by 1 unit when you go from one component to other component. So, that is always the case. This is because the multiplet has the same hypercharge, and whenever you change I3 by 1 unit, Q will be changing by 1 unit. What about the right hand electron? Charge is the same as minus 1. I3 is equal to 0, therefore, y of EL is equal to minus 2. So, that is it. There is a difference in the hypercharge assignment of, this is the right handed electron that we are talking about. There is a difference in the hypercharge of electron which is right handed and electron which is left handed. So, there is a difference between the left handed and the right handed electrons. The charges in terms of the hypercharge, there is a quantum number which makes left handed and right handed electron distinguishable, which is the hypercharge, and also the isospin. Of course, the isospin is another. These two charges, these two quantum numbers allow us to distinguish or help us distinguish the left handed and the right handed particles. That is indeed is the basic reason why they interact differently under weak interactions. okay, which is a combination of SU2L and U1Y now. Okay. The electromagnetic charge or electric charge of electron is -1 irrespective of whether it is right handed or left handed. This is the reason why we cannot distinguish the left handed and the right handed electrons under electromagnetic interaction, but they are distinguishable under weak interaction. The same story goes through for other particles as well, like you can, so the for the other leptons, muons and the tau leptons and the corresponding neutrinos, the story is exactly the same, replication of this. For quarks, because their electric charge is now different, let us consider UL, up type left charge, left up type quark has a charge of +2/3 and isospin third component is equal to +12, and that tells us that y is equal to, so relation let me write here, this q equal to I3 plus y by 2 or y is equal to 2 q minus I3, which is equal to 2 times 2 by 3 minus 1 by 2, which is equal to 1 by 6. 2 into 1 by 6 is 1 by 3. Similarly, for down type quarks, I3 is equal to -12, charge is equal to -1 by 3, y equal to, again it should be equal to 1 by 3. Let us see, q minus I3, which is equal to minus 1 by 2 into minus 1 by 3 plus 1 by 2, which is again equal to 1 by 3, which should indeed be. Right handed, q of right handed charged quark u right handed is 2 by 3, I3 equal to 0, that gives y equal to twice q, which is equal to 4 by 3. And similarly, for down type right handed, it is 1 by 3, I3 equal to 0, that will give you y equal to minus 2 by 3. Okay. So, these are the hypercharge assignments of the quark doublet and the quark singlets. The up type quark right handed will have, all the quark doublets left handed will have 1 by 3 as their hypercharge, and right handed up quark CR and TR all have hypercharge 4 by 3, and down type quark S quark and B quark all right handed have hypercharge minus 2 by 3. All right. So, this is done. We know what are the hypercharges, what are the isospins of all these particles. Now, we are in a position to construct the Lagrangian, which is invariant under the SU2 cross U1 transformation. We will follow a similar an approach similar to what we had done in the case of QED and strong interaction QCD. We will do that in the next class.